UL 774 machine learning, and today is May 1st 2020. So remember last class, we last couple of classes, we have been looking at learning theory, and just to sort of remind you quickly, looking at a setting where we're given a bunch of examples, and we can learn a hypothesis by optimizing what we refer to as training error, and what we are really interested in is the relationship of this training error with, and this is our training error, and we are really interested in its relationship with the quantity that we really care about, which is the generalization error, which is expected value of, if you draw this example xy from this underlying distribution, and this is same as the distribution from which these training examples were drawn, and then indicator of y not equal to x. Right, and recall that we used what is referred to as Chernoff bound, which was over an estimate of the Bernoulli parameter, right? We said p hat minus p, probability of this being greater than some quantity gamma is less than equal to 2 e to the minus 2 gamma square m. Right, so this was our Chernoff bound, where phi is some Bernoulli parameter and phi hat is its estimator based on m samples of this random coin toss. Okay, and then finally we said that we can relate phi hat and phi with this epsilon hat h and epsilon h by sort of this analogy, right? Or sort of this correspondence, that phi hat essentially corresponds to epsilon hat h, that is our training error, and phi corresponds to the real parameter, corresponds to the generalization error that we really want to estimate. Okay, so expressed in terms of the Chernoff bound, expressed in terms of epsilon h and epsilon hat h, right? Let me write it epsilon h minus epsilon hat h, probability of this being less than gamma, right, by way of correspondence that we established between this Bernoulli experiment repeated n times and our estimate of epsilon h using epsilon hat h, which is the training error epsilon hat h, and epsilon h being the generalization error, right? Using the correspondence we derived, or we showed that probability that this is more than gamma is less than equal to 2 e to the minus 2 gamma square, right? And this is for any given hypothesis h belonging to our hypothesis class, right? And then we use what is referred to as union bound. And remember what was union bound? Probability of a1 up to ak, where each of these a1 to ak is a set of events, right? Probability of union of these events is less than equal to probability of each of these events and summed up, right? So this holds in general, and using this for our case, right? Sort of taking union of one for all the hypotheses in our hypothesis space, right? Sort of taking the union of these events AL, where event AL is simply the event that the difference between the generalization error of LF hypothesis and the training error of the LF hypothesis is more than gamma, right? Taking union of these events and applying union bound, we get what is referred to as uniform convergence bound, which was nothing but probability that there exists an H belonging to H, which is sort of the union, such that epsilon H minus epsilon hat H, right? Here we have replaced HL by simply H, right? This is any hypothesis belonging to the hypothesis class is greater than gamma is less than equal to 2k e to the minus 2 gamma square m, right? And this k is the size of the hypothesis is, right? And equivalently, we wrote this as probability that for all h belonging to h, epsilon h minus epsilon hat h, right? Negation of what we have written here in equation 2, right? Is the negation of this would be less than equal to gamma. This probability is greater than equal to 1 minus 2k e to the minus 2 gamma square, right? So in this equation above, right, which I've written as 2 here, right, probability that there exists an edge such that uh, this difference is more than gamma is less than equal to this quantity on the right hand side, which is 2k e to the minus 2 gamma square m, which is same as saying that the negation of this quantity inside in the LHS, right, which is basically saying that for all hypotheses belonging to the hypothesis class, uh, the uh, the difference between epsilon h generalization error and the training error is less than equal to gamma. This probability has to be more than 1 minus 2k e to the minus 2 gamma square m, right? So these two are sort of equivalent, right? These two are equivalent, if you will. Okay, proceed. Let's proceed further, right? So we have probability that for all h belonging to h, epsilon h minus epsilon hat h, mod of this is less than equal to gamma is greater than equal to 1 minus 2k e to the minus 2 gamma square m, right? And just make sure that this 2k is present on the previous slide, right? In the uniform convergence bound, this is for all, because we are saying this for all hypotheses simultaneously, so this k appears from the union bound. Okay, this equivalently, right, this is where we stopped last time, can be written as for all h probability that epsilon h mod of this minus epsilon hat h less than equal to gamma is greater than equal to 1 minus delta, right? So the idea is that if this equation, right, this equation here on top, right, let me call it maybe equation 3, right? So this equation 3 here, right, holds, then I can take any quantity uh, which is less than RHS of this quantity, and it will still hold, right? So in particular, what I can say is that I can express this in terms of this confidence parameter delta, right? And this will hold as long as my 1 minus delta is less than 1 minus 2k e to the minus 2 gamma square m, right? So, or in other words, right? So this will hold, right? This second equation will hold if my delta is more than 2k, less than, or sorry, delta is greater than equal to 2k e minus 2 gamma square, right? And why we have done this is to really sort of bring it in a form that we have seen earlier, right, which is called the pack bound, right? Probably approximately correct, right? So writing it in the second in the form of the second expression above, it brings it in the form that we really wanted to have to start with, right? So there is a confidence now, right, which is sort of this delta, and this gamma is your sort of error threshold, right? And then what we are saying is that, right, to have this sort of uniform convergence, right, which is for all hypotheses, right, to bound the error, where error is the difference between the generalization and the training error, right, within this error threshold gamma, right, and having the probability of that to be more than 1 minus delta is what you really need, is this relation, right, between the four quantities. And note that, exactly where we started, right? So to achieve this pack bound, right, we need this relationship between these four quantities, where once again delta is your sort of confidence parameter, uh, k is the size of hypothesis class, right? Remember, and we are in the regime of finite sized hypothesis. Gamma is your error threshold, right? And m is number of training examples, confidence parameter. Okay, and we will, just rewrite this equation in multiple forms to get dependence of one parameter on the others, right? So for example, let me use different sort of color here, right? So one way to write this is exactly the way we have written here, that that to get a certain back bound, right, which is the probability of, for all hypotheses having the difference between the generalization and the training error less than gamma, less than equal to gamma, the probability of this being more than 1 minus delta will hold if our delta is greater than equal to 2k e to the minus 2 gamma square m, right? So this particular way of writing this equation is saying that, right, if someone gives me k, right, which is the hypothesis size of the hypothesis class, right, and gives me a certain error threshold that I want to achieve, which is gamma, and a number of examples, which is m, then my delta, right, sort of the confidence parameter, should be more than this 2k e to the minus 2 gamma square, right? And note that it sort of increases, right, right, delta increases with increasing uh, size of the hypothesis class, right? So in some sense delta increases, which means 1 minus delta decreases, right? So you have sort of lower confidence in some sense, right, as your hypothesis class increases, right? And on the other hand, right, as m or gamma, right, either of them increase, right, delta decreases, right? So with larger number of examples, right, or having, if you have a larger error threshold, then right, delta decreases, which means 1 minus delta increases, so you can have a higher confidence in your bound, right? And another way, right, so this is one way to write it, right? So another way to write this would be to write this in form of right, gamma and m, right? So let me just rewrite it as delta by 2k is greater than equal to e to the minus 2 gamma square m, right? Which means that if I take log on both sides, right, we will get log delta by 2k is greater than equal to minus 2 gamma square m, right? Let me sort of continue this on the next slide. So, writing that expression again here, we have delta greater than equal to 2k e to the minus 2 gamma square m, right? So this is our sort of first expression. Then rewriting it, we get delta by 2k is greater than equal to e to the minus 2 gamma square m, right? Which implies that if I take log on both sides, log of delta by 2k is greater than equal to, because log is an increasing function, so I can take log on both sides without changing the direction of inequality, right? So it becomes minus 2 gamma square m, right? And then I can sort of negate both sides, right? So log of 2k over delta, and then reverse the inequality sign. So this will be 2 gamma square m, right? Now, which will give rise to two different expressions. So one will be in terms of gamma square, right? So we'll get gamma square is greater than equal to 1 by 2m log of 2k over delta, which means that gamma is greater than equal to 1 by 2m log of 2k over delta square root, right? And this is sort of our second sort of dependence, right? So this was our first dependence on the top, right, which is telling us what delta to choose to get a certain pack bound in terms of our parameters k, gamma, and m. And now we are saying, another way to express the same, right, dependence is in terms of writing what gamma do we need to choose, right, for a given m, k, and delta, right? And again, I think intuitively, right, when you go back, that it makes sense, right? For example, right, as you increase a number of examples, right, right, your gamma decreases, right, the bound on the gamma sort of decreases, right, which means that you are now allowed to have lower error threshold as you have more number of examples, right? On the other hand, if you have a larger hypothesis class, right, the bound on gamma increases, right? So you will now have to have larger error threshold. And similarly for delta, right? If your delta increases, right, if you are willing to have sort of right, delta increases, 1 minus delta decreases. So if you are willing to have lower sort of confidence threshold, right, which is 1 minus delta, right, then you can afford to have uh, uh, right. So delta increases, 1 minus delta decreases, right, and as delta increases, gamma increases, right? So you can have a better sort of or lower error threshold, right? And think about it more as you go back, okay. And the last one, right, which is in terms of m, we can write it as m, right, from the equation above, the equation written here too, right? So we can write it as m greater than equal to 1 by 2 gamma square log 2k over delta. I hope I have written it correctly. Yeah, right. So this is our third dependence. And now this is saying, for to achieve a certain pack bound, right, which we had shown on the previous slide, right, how many examples are required. And again, once again, make sure that the dependence of m on gamma, k, and delta make intuitive sense. So what have we done here, right? Just to summarize, right? We want that probability for all hypotheses belonging to our hypothesis class, and we want to bound this probability that the difference between the training and the generalization error is less than equal to gamma, right? And this probability should we want it to be at least 1 minus delta, right? And this bound will hold, right, if we choose the parameters, right, using either of sort of equivalent expressions, which is we can say that delta should be greater than equal to 2k e to the minus 2 gamma square m, right? So this is the first one. Or we can say that the gamma should be greater than equal to 1 by 2m log 2k by delta and square root of that. So this is the second one. Or we can say that m is greater than equal to 1 by to gamma square log 2k by delta, right? So to achieve the above sort of back bound, right, which is also sort of the referred to as uniform convergence bound, right? Because it is stated in terms of all hypotheses belonging to the hypothesis space, right? We can choose either of these equivalent expressions where one parameter is written in the form of the value or the bound on the values of one parameter is written in form of the other parameter. Okay, great. So this is great. Then finally, right, before and remember, this is all in the context of finite hypothesis classes, right? And before we go to infinite hypothesis classes, I want to derive one more result, which I think is quite important in this context, and which is, this is fine, right? And this uniform convergence bound, this is for all hypotheses in our hypothesis class, right? But really, if you think about it, right, what we are really interested in is that given this data, right, xi yi I equal to 1 to m, right? I am going to sort of minimize my training error or some proxy for training error, right? For example, it could be some kind of squared error, right? But some proxy for training error, and I'm going to get some hypothesis h hat, right? And let's say h hat is exactly the hypothesis which minimizes my training error, right? So hypothesis no h hat is exactly the hypothesis which minimizes this error, which is yi not equal to hxi, right? Sum over all examples and 1 by m, right? So this h hat is in some sense, taking our min over right, every hypothesis in the hypothesis class, and whatever hypothesis gives me this minimum training error is what I get, right? And as I said, right, there is some uh, uh, there's a little bit of detail here in terms of we may optimize a slightly different error, not exactly training error, but let's sort of ignore that for a moment, and let's say our training procedure gives you the hypothesis h hat which minimizes the training error, right? And that's exactly right, typically we will do in practice. And corresponding to that, right, we may get our error which is epsilon hat h hat, right, which is exactly this, right? So this is sort of the expression written here on the right is exactly right. So this is training error of my hypothesis h hat, right? And this is sort of the best you could do on the training data, right? But what will happen is that right, in reality, right, when you go and apply this h hat, right, this is exactly this, right? And right, where h on the right side is substituted for h hat, uh, right? But what will happen in reality is that you will actually take this h hat and apply it to real data. And so what we are really interested in is generalization error of h hat, right? So this is our generalization error of h hat, right? And more so now, right? In fact, let me continue this on the next slide. So we have h hat, which is best on training data, right, which minimizing our training error. And what we get here, or what we are looking, uh, right, what we really minimize was the training error. And this is the training error of h hat. But what we are really sort of interested in is how well this h hat generalizes, right? So this is the generalization error of h hat, right? So in other words, what we are saying is that we obtain a hypothesis h hat, which is which does well on the training set. In fact, it does sort of the best on the training set. But what we really care about is how well it does on the test set, or on unseen examples, which is exactly captured by the generalization error. Right now, right, let us assume that there is some hypothesis H star, right, which is which again belong to our hypothesis class, right, which does best on the which is the overall best in terms of the generalization error, right? So there has to be some hypothesis, right? It's a finite hypothesis class, right? So there has to be some H star belonging to H such that H star minimizes our generalization error, right? And in some sense, right, this H star is exactly right what we are interested in finding out, right? Interested in finding. Right, right, because if we someone gave us access to generalization error and sort of efficiently computed for every hypothesis, then we would just simply output H star, right? But what we have instead is training error, which is a proxy for the generalization error. And exactly right, we want to understand how good of a proxy it is, the training error for the generalization error. And in particular, right, if we optimize the training error, we get H hat. And then what we really are interested in is understanding how good or bad is this H hat on the generalization in terms of its generalization. And in particular, right, if you will, right, if you think about it carefully, right, we are interested in is how different is the generalization error of H hat from the generalization error of H star, right? So this is best that we can do, and this is what we achieve by minimizing or optimizing over training data, right? And if we could bound the difference between those two, right, then we would have sort of a confidence that although we optimized on the training data, but we are not very far in terms of what is overall best or global sort of optimal you could do, right, if you were sort of given infinite capacity or capacity in terms of evaluating everything on the in terms of the generalization error, right? So let's now try to derive this. So the way we will do this is we will say epsilon of H hat, um, right, is less than, right. So this is now generalization error of H hat, and we are going to first transport this error to sort of the training space by using uniform convergence bound, right? Because we know that the training and the generalization error for in fact for all hypotheses, right, are within the bound gamma, right? And there is a certain probability, that is 1 minus delta, that it holds at least with 1 minus delta. Therefore, we can say that this is less than equal to epsilon hat of H hat plus gamma, right? And this right, whatever I'm writing here is with probability at least 1 minus delta, right, where delta is sort of is the way we have defined on the previous slide, right? So whatever I write in this inequality, right, or this sort of set of inequalities will hold with probability at least 1 minus delta, right? And this comes, right, this particular expression comes once again from the fact that we have uniform convergence bound. Therefore, the training error of H hat is within gamma distance of the generalization error, or rather generalization error of H hat is within gamma distance of the training error of H hat, right? And now this is less than equal to epsilon hat H, right? And smartly enough, right, we will now take it to the training error of H star plus gamma. And why is this, right? This particular, let me call it number one, and this is number two, right? So number one holds because of uniform convergence bound applied to H hat here, and number two holds, right, because right, H hat was the best on the training data, right? Because H hat was the best on the training data, therefore the training error of h hat has to be less than equal to the training error of any other hypothesis, in particular h star, right, which happens to be but based on the generalization. In terms of generalization, but that's a sort of a different story, right? But at least on the training data, right, because h hat is the best, therefore, right, epsilon hat h hat plus gamma must be less than equal to epsilon hat h star plus gamma, right? And as some of you might have guessed, right, in the next inequality, right, we will now take this training error over h star to the space of generalization errors, and we will write it as this is less than equal to the generalization error of star plus gamma plus gamma, right? And let me just put a bracket here, right? And this is inequality number 3. And why does this hold, right? Right, in the right hand side, right, what I have done here, right? So one of the gamma, is just copied from from epsilon hat h star plus gamma to the right side. But what I've done here is epsilon hat h star must be less than equal to epsilon h epsilon of h star plus gamma. Why? Because now applying uniform convergence bound on h star, we know that the training error of h star has to be within gamma distance of the generalization error of h star, right? So I marked also, right? We have applied a sort of uniform convergence bound on h star, saying that the training error of h star has to be within gamma distance of generalization error of h star. Therefore, we get that epsilon hat h star is less than equal to epsilon h star plus gamma, and the second gamma is just copied over, and we get is essentially epsilon of star plus 2 gamma, right? And all this holds with the probability at least 1 minus delta. And I'll sort of write it again on the next slide. Once again, what we have done here is that we have given this bound that the generalization error of h hat, which is our best on training, is less than equal to, right, using bunch of inequalities, right, this is less than equal to epsilon of h star plus 2 gamma, right, where h star is sort of best overall, right, in terms of its generalization error, right? And this is the sort of the bound that we have gotten or obtained on h hat, right, in terms of its generalization error being, at most 2 gamma plus the best that we could do overall, right? And this holds, right, above result holds with probability at least 1 minus delta, right? So with probability at least 1 minus delta, that we can say that above result will hold, right, which sort of bounds the error of the best on the training in terms of the overall generalization error. And recall that here once again delta is greater than equal to 2k into the minus 2 gamma square m, right, where the symbols are as defined earlier. And right, this could also be expressed in terms of gamma, right, which is gamma is greater than equal to 1 by 2 m log 2k by delta square root, or this could also be expressed in terms of m 1 by 2 gamma square log 2k by delta, right? And this is just different ways of expressing uh, these dependencies, right, in terms of delta, gamma, or m, right? And if we choose our parameters in this manner, then we are able to show this important result that the generalization error of what does best on the training is bound by 2 gamma plus generalization error of overall best hypothesis, right? So this is an important result of back learning, right? And using the idea of uniform convergence bound, right? And the next sort of in the next slide, now we will look at sort of generalization of some of these results to the case of infinite sized hypothesis classes. Okay. I just want to make one remark before we proceed, to make sure that we understand what I've written here on the previous slide well, which is that we have said that epsilon of h hat is less than equal to epsilon of h star plus 2 gamma. And the last result I wrote that it holds with probability 1 minus delta, and then I'd written, the last sort of expression I'd written m is greater than equal to 2 gamma square 2k by delta log of this, right? So this particular form, which is sort of the last third one, is saying that if you want this to be true, right, which is bound the generalization error of h hat, to be within right 2 gamma distance of generalization error of the H star with probability at least 1 minus delta, then what we need to do is right in this particular way of writing the expression, we are saying that if we choose number of examples to be more than this quantity on the right hand side, then we'll be able to achieve this bound. And similar sort of argument holds for when we are saying choose delta to be more than this for this to hold with this probability, or uh, choose gamma to be greater than equal to the error threshold to be greater than equal to the quantity which we had written on the previous slide for this bound to hold with probability 1 minus delta for a given number of examples, right? So you could sort of argue about this bound in terms of either of these gamma, m, or delta parameters. I just wanted to clarify. So next we come to an important sort of topic or important extension, which is dealing with infinite sized hypothesis classes, right? And here we will introduce the concept of what is referred to as VC dimension of a infinite hypothesis space, and in some sense this will be sort of a proxy for the size of the hypothesis class, right? And VC stands for Vapnik Chervo Chervonensis dimension, right? And this is named after the Russian mathematicians who are sort of the inventors of this concept. And this is a very important concept in learning theory, right? So very important concept in learning theory. Okay, so before we proceed any further, let me sort of give you the intuition again, right? So in fact, right, almost all the right or most of the learning problems that we have dealt with, right, maybe with the exception of decision trees in certain settings, our hypothesis classes are in fact right um, infinite sized, right? And why is that, right? Just recall this simple monkeys and chimpanzees example, right? And these were our chimps class, and these were our monkeys class, right? The negatives, and we were looking, let's say, for a linear separator, right? So this could be done using either your SVMs, right? You could do it using your logistic regression, right? Or you could even do this using neural networks, right? Right, any of these sort of algorithms, right? Or even let's say GDA, right? Each one of those, let's say, right, has a way to learn this linear decision boundary, right? But the question is, what is your hypothesis space, right? So in this case, this is the set of all linear separators, right? And in R2, right, this is simply set of all lines, right? But in Rn, right, in general, this will be a set of hyperplanes, right? This will be set of you know, all hyperplanes in the Rn or the n dimensional space, right? So that will be your hypothesis class, and clearly this is infinite sized, right? So in any of these cases, right, even in R2, right, there are infinite many number of lines which we could uh, essentially, you know, discover. In fact, right, if the data is linearly separable, there is, you know, infinite number of lines, right, which lines, right, which have the same training error, which is zero, right? And what is interesting is that, maybe I'll show more on the next slide, is that now how do we really compare sort of the representational capacity of this hypothesis class with let's say, you know, quadratic classifiers, right? So this is another hypothesis class, right? Let's say again, maybe H prime, right, which is, you know, set of all quadratic separators, right? And whereas intuitively we do understand that this H prime is probably more representationally more sort of powerful than H, right? But you know, but both are infinite size, right? Uh, so although both are infinite size, right, because there is an infinite number of separators which are lines, and there is also infinite number of um, separators which are quadratic, but right, in fact we know that the number of or the set of quadratic separators is a strict superset of, you know, linear separators, right, in this case, right? So and how do we really sort of quantify this in terms of you know, the representational power of a hypothesis space? For example, in this case, right, this intuition that a quadratic set of all quadratic separators is representationally more powerful than the set of all linear separators, and that is where, you know, the idea of VC dimension will come in, that we'll be able to show that there is a number, or there is a dimension that we associate with, you know, many of these hypothesis classes, right? And this dimension of let's say a quadratic set of all quadratic separators is, you know, hopefully more, right? In fact, it is more than the VC dimension of all linear separators, right, for any space Rn, right? And that is where we will deal with this topic of VC dimension. I just want to mention that in this class we'll probably prove, you know, the relationship, or will rather be able to show that in 2D, right, the VC dimension of quadratic classifiers is strictly more than linear classifiers, and maybe the result for n dimensions will be left for, you know, as a future exercise, right? But let's start with the right. Let's start with some basic notation that will be important for defining the concept of VC dimension, right? So let me write it on the right side, right? So X, assume that X is the set of all instances, right? So X is the set of all instances. For example, X could be uh, your Rn, right? Which means that your each Xi will belong to Rn, right? So this is X, but in general, I guess it doesn't even have to be Euclidean space, but I think for our discussion will our examples will be in the Euclidean space. But I think that the theory is more general to sort of any set of X instances. Okay, then we will also define H to be our hypothesis class, right, which typically will be infinite dimensional, right? But again, this the idea is fairly general, so you could have finite or infinite dimensional, right? This VC dimension is, you'll see, is defined for both, but primarily we'll use it for defining it for um, infinite sized hypothesis classes, where this is primarily where we need this terminology. um, then we will also define a set S, right? Curly sort of S, which is a subset of all instances. And typically this will be denoted as x1 to xd, right? So this is a subset or a set of the instances, right? A set of the instances in the instance space. Okay, and then given an S, right? Given a subset S of instances, right, we will define also a labeling which is y1 to yd, right? These are just like class labels where we have seen earlier, where each y belongs to 0 to 1, right? And we will refer to this as a labeling. And why is that? Because note that there is no notion of training examples here, right? We are simply given a set of instances, right? And we are given these the instances, for example, and we'll define the concept of a labeling, which is an assignment of 0 or 1 to each of these instances, because we are dealing in the binary classification setting, right? And note that for a subset of size D, there are two to the D possible labelings, right? And we'll sort of argue about all these two to the D possible labelings, and wherever required, we'll denote this by this set curly L, uh, right? And note that in some sense this the set of all possible labelings depends on the set S, but maybe we just dropped the subscript S to be right, to make it notationally simple, right? So X is the set of all instances, H is the hypothesis class for which we are trying to find the VC dimension, S is a set, right, or a subset of D instances where D is some finite number, and y1 to yd is a particular labeling which is sort of assigning a label to each point. We'll see an example. And L, this curly L, right, you can also write subscript here to S, right? This is the set of all possible labelings which whose size is to the 2 to the D, because each example could get a 0 or a 1, right? It's again binary, the setting of binary classification. Okay, so given this notation, now let us understand the idea of shattering, which will be essentially, which will be right, quite important to the concept of VC dimension, right? And maybe let me use a different pen, right? Let's say we are in R2, right, and we are given three instances. Let's say x1, and this is some other point x2, and this is some point x3, right? And right, so the idea of shattering, uh, right, and when we define shattering, right, we are given an instance space which is sort of R2 here, and also you are given a hypothesis class, and let's say this is all the set of all linear right, all linear separators, right? All lines, right, or right, in general will be sort of hyperplanes, but in R2 this is all, let's say, lines or linear separators, right? And then the idea of shattering says that given, let's say, a subset S of points, which in this case is x1, x2, and x3, right? We say that the hypothesis class H shatters the set S, right, which is a subset of points, if for all possible labelings y1, y2 up to yd, there exists an H belonging to H such that H of xi is equal to yi, right? Or right, we also say that H realizes labeling y1, H realizes the labeling y1, y2 up to yd, right, where d is 3 in this case, right? So let me sort of give you the intuition, right, of this idea of shattering, right? So given these 3 points, so what we are saying is that this particular space of 3 points is shattered by this linear sort of hypothesis class, right? The set of all linear separators, if if we can show that for any possible assignment of, let's say, 0 or 1, or let's say positive and negative, and positive to these points, right, there is a line which realizes this labeling, right? For example, for this positive, positive, and negative, right, I could draw a separator like this, right, and everything on this side is negative, everything on this side is positive, right? So this particular hypothesis is able to achieve this particular labeling, right? And further, right, maybe there is a different labeling now, right? Let's say this is positive, but this is negative, and let's say this is positive, right? So this particular labeling can be achieved by this purple separator where everything on the top is positive and everything on the bottom is negative, right? Um, right. Let's just try one more example, right? Maybe with yellow color, right? So let's say I could have all positive. So this is positive, and this is positive, and this is positive, right? And then clearly a separator would simply be this separator, which essentially assigns everything on the upper side as positive and everything on the bottom side as negative, right? And in fact, you can show that for 2 to the 8, let me use a different color, right? In this case, for 2 to the 8 different 2 to the 8 different labelings, right, that we have, right, there is a line, right, there is a separator which can achieve that labeling, right? Right, so given a labeling, um, right, if we can find a hypothesis in the hypothesis class which achieves that labeling, right, and if this is possible to do for every possible labeling, right, which is 2 to the 8 in this case, right, that is that there exists a hypothesis which can sort of achieve the labeling for all possible labelings of the given set of points, then we say that this S is shattered by this hypothesis class H, right? So this is the idea. Okay, so let's sort of revisit our idea of shattering that we have shown on the previous slide, right? So we have sort of argued that if we have 3 points, right, let's say these 3 particular points, and this is our set S, right, and then any sort of labeling that we give to these 3 points can be achieved, right, by hypothesis class, which is H, which is the set of or the set of all linear set. This is the set of all hypotheses which are linear separators, right? And right, for any given labeling, we are able to achieve that labeling through some hypothesis in this hypothesis class, which is set of all linear separators. Therefore, this set S is shattered by H, right? Now let's make it slightly more interesting, right? So we can ask two questions. So the first question is, right, is it the case that any set of 3 points in 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 R2, right, can be shattered by H, where H is the set of all linear hypotheses, right? And the answer is no, right? And why is that? Right, let me draw it here in a different color, right? Suppose I take my points to be collinear, right? So if my points are collinear, and then clearly, right, if I assign this to be positive and this to be positive and this to be negative, right, then right, there is no H belonging to capital H such that labeling this particular labeling on the left, right, this particular labeling on the left is achieved, right? Right, so if my points are collinear, right, if they are on a line, right, then there is no hypothesis in this linear hypothesis class, right, which can actually achieve this labeling, right? In fact, you can show that right, any given set of 3 points can be shattered by this linear hypothesis class unless they are collinear, right? And this idea will sort of become important, right, as we define VC dimension. And note um, that this is sort of a adversarial game that we play to show that uh, right, where the adversary sort of tries to uh, right, give me, right, given a set of set S of points, right, the adversary tries to give me a particular labeling, which is let's say y1 and up to yd, right, for a set of d points, and then my job as sort of someone who is trying to prove that it can be shattered is to find a hypothesis H belonging to H, which achieves this labeling, right? So there is sort of an adversarial game here, right? That my adversary gives me a particular labeling, and then I try to find a hypothesis, and if I sort of succeed in this game, right, for all possible such labelings, then I can show, I'm able to show that the set of points, given set of points in is in fact shattered by my hypothesis class, right? So in this case, the set of points on the top, which is not collinear, right, in fact can be shattered by this H. But if I take my points to be collinear, right, so this particular set of 3 points which are collinear cannot be shattered by H. Okay, so let's make it slightly more interesting now, right? So what happens if I take 4 points in this 2D space, right? So if I take, let's say, x1, x2, x3, and x4. Now the question is, right, can this set S be shattered by this linear hypothesis class, right? So can S be shattered by this linear hypothesis class? And in fact, the answer is a big no, because I could assign, these sort of opposite points to be positives, and this opposite points, the remaining opposite points to be negative, and it is not very difficult to show that there does not exist any hypothesis in this hypothesis class, right, which can achieve this particular labeling on the left, right, where this means this particular labeling, right? And right, in fact, right, I have not really shown this for uh, any 4 points in general, but you can actually show that, right, any set of 4 points in R2 cannot be shattered by hypothesis class H, right? And this is interesting because this will lead us to the definition of VC dimension, right? And in fact, we can show that, right? It's not very difficult to show. This is actually similar to the XOR example, right? And we saw that no, a linear separator could not really achieve that separation for XOR, and this is a very similar example. And you can show that this is true for any set of 4 points, that there is a particular labeling that cannot be achieved. Therefore, no set of 4 points uh, can be shattered by a linear hypothesis class. But right, in fact, we will try to argue in the next class that a quadratic separator can actually achieve this labeling. That maybe let me argue that in the next class. But let me just give a preview into what is VC dimension. Right. So given a hypothesis class H, right, which is right, and instance which is sort of defined over this instance space X, right? So with respect to an instance space X, right? So given this hypothesis class, which is defined over this instance space X, right? So we see dimension of H, uh, uh, right? We see dimension of this hypothesis class is simply is the size of the largest set S, uh, uh, right, largest set S, which is subset of the instance space that can be shattered by H, right? So for example, in the above case, right, there is a set of size 3, right, which can be shattered. Note that we are looking for some set of a certain size that can be shattered, and then we'll say the VC dimension is at least that much, right? So in this case, there is a set of size 3 which can be shattered, so VC dimension is at least 3. But if we could prove, right, in fact, and we have sort of argued that there is no set of size 4 which can be shattered, therefore VC dimension is strictly less than 4, or in particular combining these two together, the VC dimension is exactly equal to 3, right? And in the next class, we will see that this is essentially, this VC dimension really captures the power of representational power of hypothesis class. For example, a quadratic separator in this case will have a larger VC dimension because it can separate out sets of size 4 or maybe more. Thanks.